Okay, troops, impulse and change in momentum today. When an object experiences a force for a short period of time, it experiences an impulse. That causes its momentum to change. We can derive a relationship for impulse and change in momentum. We start off with Newton's second law, F equals ma, and our basic relationship for acceleration. If we combine this acceleration equation into F equals ma, we end up with F equals mv minus u over t, multiplying both sides by t, and then multiplying through the bracket, we get ft is mv minus mu. That is on your relationship sheet. The right hand side is change in momentum in kilogram meters per second. The left hand side is impulse, measured in Newton seconds. And impulse is the average force acting on the object times the time of contact. We're going to do a little experiment to measure that average force. The average force acting on a ball. Now here's the apparatus, and also the method is going to be listed here, so you can pause that if you like and have a look at it. But basically we're going to measure the time of contact between a metal cue and a metal ball. And then we're going to measure the speed of the ball after it has been hit with the cue. And from the change in momentum and the time of contact, we're going to use the relationship that we've just derived. That's Ft equals mv minus mu. And we're going to calculate the average force on the ball using that relationship. So, here we go. Okay, troops, another exciting higher physics experiment here. Today, we're going to try and calculate the average force that we exert on a ball when we hit it with a cue. And we're going to try and do that by measuring the change in momentum of the ball. Its initial momentum is 0, and then we're going to measure its velocity when it goes through the light gate using a TSA. We're going to measure its mass. And we're going to measure the time of contact between the metal cue and the metal ball on the metal track by having the cue and the ball and the track all connected into a circuit where we can measure that time of contact just by tapping the ball. So we have to set this up to measure a very fast time. Okay, ready to go. It's waiting. Next, we're going to use this TSA computer to measure the speed of the ball. So let's set that up to measure speed. Now, we're going to make one measurement of speed. One. The mask size is the diameter of the ball. That's a 4 centimeter ball. So let's put in 4 centimeters. And we're ready to go. So, a 4 centimeter object going through that light gate will allow that TSA to work out the speed that it's going at. The only other piece of information we need is the mass of the ball. Okay, there's the mass of the ball. So put the ball very close to the light gate so that we minimise the effects of friction slowing the ball down once it's been hit. Remember, the law of conservation of momentum states that the total momentum before equals the total momentum after in the absence of any external forces. So let's go. That one's waiting. That one's waiting. We're going to measure the time of contact and the velocity of the ball. Here we go. Metal cue, metal ball, light gate. There's our results. Time of contact, 1.3 milliseconds. Speed, 0.49 meters per second. Let's see how we got on. Right, so here's our experimental setup and the measurements that we made. The mass of the ball was rounded up to 21 grams. The time of contact, 1.36 milliseconds. And the final velocity, 0.49 meters per second. We'll be using all those measurements in this relationship. Remember, mu is the initial momentum. It was 0 because the ball was stationary. mv, the final momentum, and t, the time of contact. That will allow us to work out the average force. Let's substitute in those values then. So time of contact, 1.36 milliseconds. A mass of 21 grams and V 0.49. Initial momentum was 0 because the ball was stationary, and then rearranging to find F. So divided by the time of contact, and we get 7.6 newtons. That's the average force acting on the ball. That's impulse causing a change in momentum.